So the thinking towards the end of the 19th century was that there is a preferred rest frame, this ether, and there must be a way to figure out what this reference frame is. So by that we mean the Earth is moving around the sun, and of course the sun is moving around the center of the galaxy. So since the Earth is moving, we must be moving with respect to this ether, this preferred reference frame. And at different times of the year, we would be moving in a different direction with respect to this preferred reference frame or this ether. Okay, so at a later point in the year, assuming that the sun hasn't changed its position significantly, we would be over here, and we would be moving in the opposite direction with respect to the ether. So at different times of the year, okay, we would be moving in different directions. So for simplicity, let's just assume that the rest frame of the sun is this preferred reference frame. And you can clearly see that at different times of the year, we would be moving in different directions with respect to this ether. Now, people tried to conceive of an experiment which would detect the motion of the Earth through the ether. Okay? And the experiment which was designed to detect this motion of the Earth relative to the ether, that is to detect the preferred rest frame, was called the Michelson-Morley experiment. So here's the idea for the Michelson-Morley experiment. Let's start by viewing the world from this preferred rest frame, this ether rest frame. Then the Earth at any time is moving with a velocity v Earth. We don't know what this velocity is because we don't know what the rest frame of this ether is, but it's moving with some speed relative to this ether, and that speed is not constant clearly because at different times of the year we are at different positions around the sun, so therefore we're definitely not at rest with respect to this ether. At least at all points in the year we cannot be at rest with respect to this ether. And now let's imagine that we consider light rays, again in the reference frame of the ether. So in the ether reference frame, let's take light which is moving in different directions. Okay, so according to the conjecture at the time, in the ether rest frame, the light traveling in every direction has a speed c. Okay, no matter which direction you look, the speed should be c. But what that means is, according to the principle of Galilean relativity, if we took an observer moving along with the Earth, that observer should measure different speeds for the speed of light depending on which direction the light beam was going. That is, if the observer moving along with the Earth were to ask what is the speed of this light beam, since they're moving along with that light beam, they would measure the speed of this light beam to be lower by this amount, c minus VE. Similarly, if they asked about this light beam, they would measure a higher speed because they are moving away from this light beam, so they would measure a speed c plus VE in this direction. Okay? So, different directions of light beams would have different velocities as measured by an observer on the surface of the Earth. So the idea of the Michelson-Morley experiment was to try to take measurements, or effectively measure, the differences between the speed of light in different directions. That is, try to measure the speed of light as seen by an observer on the Earth in one direction and another direction, maybe let's say an orthogonal direction. And the speed of light in these two directions should appear to be different to an observer on the Earth. An observer on Earth should measure different speeds of light in different directions. So in principle, if you measured the speed of light with respect to the Earth in many different directions, okay, so you made many different observations of this, you know what the speed is in the ether frame, then you could use that to determine the relative velocity between the Earth's frame and the ether frame. So using these many different observations, okay, making many different observations of the velocity of light in the Earth reference frame, and knowing the speed in the ether frame allows you to determine the relative velocity between the Earth's frame and the ether frame. So this would be a detection of what we would call ether drift, that is our motion with respect to the ether. Okay, so this experiment was designed to measure the difference between the speed of light in different directions, and the result would be a detection of the ether drift. So let's see the setup for this experiment. So the idea for this experiment was to use what is called an interferometer. So you set up a light source which emits light which is coherent, that is, it has a particular wavelength lambda, which is the distance between two peaks of the electromagnetic wave as it propagates to the right. And in the way, you set up a beam splitter. And what this beam splitter does is it reflects half the light in this direction, and it transmits half the light in this direction. Okay, and the light beams travel some distance L before they encounter a mirror. So this mirror is placed at some distance L, away, and this is a reflecting surface. And similarly, there's another mirror over here. So the light beams travel some distance and then they get reflected back, travel some distance and get reflected back. And you arrange it in such a way that effectively this length L is the same as this length L over here. So the light beams travel exactly the same length. They travel a length 2L between going forwards and backwards. They travel a distance of 2L. And then you recombine those two beams. And since light is a wave, these two beams should interfere with each other. And what you do is you now try to detect. Okay, so you put a detector here. And you try to measure the the interference pattern between these two light beams. Okay, so let's examine that setup again. You send light beams, a single light beam to the right. It's a coherent light beam with a single wavelength lambda, and part of it is split in such a way that it moves to the right. Another part is sent upwards, and both these different split light beams now, they travel the same path length. Okay, then they're made to recombine, and then you detect their interference in a detector. Now, if they've traveled exactly the same path length, now the speed of the light, okay, in this direction, let's suppose, is v1. But if the speed in this direction is v2, which is different from v1 because we are drifting with respect to the ether, light should be traveling to the right with some speed v1 and upwards with the speed v2. And these speeds v1 and v2 should not be the same. Okay. Otherwise that would be inconsistent with the idea of Galilean relativity applied to light. So now the number, you can count the number of so you can determine now what the phase difference would be between these two different light beams when they are recombined. Okay, once they recombine, they do exactly the same thing. So they're not going to pick up any phase difference over here. The phase difference just comes from the fact that these light beams had different speeds when they were moving in this direction to the right and this direction upwards. So if you ask what is the phase shift of the light of light beam 1, which moves to the right and comes back, the total phase shift, the change in phase, would be proportional to the path length traveled divided by the speed of the light beam as it went to the right and back. Similarly, for light beam 2, the total change in phase as it goes up and comes back down would be, again, the path length divided by the speed. Okay, sorry, proportional to. So you can show that that proportionality constant here would depend on a property of the light beam itself, which would be the frequency of the light beam. So that proportionality constant would be omega. Where omega is the frequency of this light beam that you originally transmitted. Okay, so this frequency is the same. This frequency does not change for the light beam which goes this way as well as that goes this way, because the frequency determines the vibrations in time. Okay, and that vibration in time is what's sourcing the light beam that's moving to the right or moving up. So the phase difference that's arising when this light beam moves to the right and when it moves up is arising purely from the fact that the speeds in these two directions are different. Okay, because the path lengths are exactly the same, the frequency of the light in both directions is exactly the same. So the only thing that can create a phase difference is the fact that the speeds of light are different in these different directions. So at your detector, you will detect a phase difference, delta phi, which would be the phase picked up by the first light beam, which moved to the right, minus the phase picked up by the second light beam, which moved up and back down. And that phase difference would be omega times 2L 1 by V1 minus 1 by V2. Okay, so there would be a phase difference just from the fact that the speed in one direction is different from the speed in another direction. So different speeds in different directions would create an interference pattern. Okay, so the goal was, if you arrange for these path lengths to be the same, can you detect such an interference pattern? I just want to take a minute to show you how to get this phase difference between two light beams. So let's suppose that you have two beams of light which start out in phase. So the waveform for this beam of light looks like this. So we'll write it as A1 sine of K, let's write it as omega times T minus K times X. And for the second one, we will use some other amplitude. The amplitude doesn't matter, we're interested in the phase. Sine of omega T minus Kx. Now, the frequencies omega are the same, okay, because the light is sourced by the same, let's say the same source. However, these k's, which are related to the wavelengths of the light, could be different if the light travels with different speeds. For example, if as light travels through different mediums, for example in glass, right, we know that the wavelength changes due to, and this causes the phenomena of refraction. So the relationship between k and omega is of this form. Omega is v times k. So in general, if this light beam now travels with a speed v1 and this light beam travels with a speed v2, k1, which is this wave number over here, which is 2 pi by the wavelength, that would be related to omega as omega over v1. And similarly, k2, which is this wave number over here, would be 2 pi over whatever this new wavelength was, which would be omega over v2. Okay, and you can see that initially at time t is equal to 0, and let's assume that they start at x is equal to 0, they are completely in phase. That is, this phase and this phase are the same. However, after they travel some distance, okay, after I wait some amount of time and then I compare their phases, so the times are the same. So the only phase difference that they would pick up is due to the different path lengths that they would travel because they have different speeds. So if I compare them at the same time in the future, what I would see is that the first wave has picked up an extra phase which would be k1 times the path length that it has covered, and k1 times the path length that is covered would be omega by v1 times L. And for the second wave, similarly, we can write down the phase that it picks up as k2 times L, which would be omega over v2 times L, assuming that they cover the same length, but they're just traveling at different speeds. So now the phase difference of the Michelson-Morley experiment can just be written as omega into L 1 over v1 minus 1 over v2, where the first term is due to the phase difference picked up by the first wave, and the second term is due to the phase difference picked up by the second wave. So what this interference pattern would lead to would be things like this. You'd see bright spots, then dark spots, then bright spots, dark spots, bright spots, and dark spots, corresponding to constructive interference, where the phase difference was an integer multiple of 2 pi, and dark spots, which would correspond to where the phase difference was an odd multiple of pi. Okay, and this phase difference was purely speculated to arise from the fact that the speed of light must be different in different directions since we're drifting with respect to the ether. Now, in reality, when performing this experiment, the thing to keep in mind is that it's not really always possible to arrange for the two path lengths to be exactly the same, right? Because you need to do this very precisely. So if you call this length L2 and this length L1, it's not possible to arrange for them to be exactly the same. So you will get an interference pattern even if the velocities v1 and v2 were the same, just because of the fact that your experimental setup doesn't allow you to set equal path lengths. Okay? However, what should happen is that as you rotate the apparatus, so as I imagine making a rotation of this, the path lengths continue to stay the same, but the velocities or the speeds v1 and v2 will change because now the light is moving in a different direction relative to the velocity of the Earth in the ether. Okay? So as you rotate the apparatus, what should happen is that this interference pattern that you saw should shift either to the right or to the left. So the fringes, the bright and dark spots, will shift either to the right or left as you rotate the apparatus because of the fact that the speeds v1 and v2 will change as you rotate the apparatus. So the goal of the Michelson-Morley experiment was to look for this fringe shift. So the fringe shift goal was to look for the fringe shift as a sign of ether drift. Now, Michelson and Morley did this experiment in 1887. Their apparatus was very simple and set up on a tabletop. And they tried to look for the shift in this interference pattern. And they found something surprising. No matter how they rotated their experiment, there was no shift in the interference pattern. When they looked at it at different times of the year, they could again find no shift in the interference pattern. This result was quite stunning because no one expected this at all. People speculated on all kinds of other ideas. For example, there was a theory of so-called ether drag, that as the Earth was moving through this ether, it was dragging the ether along with it. And so therefore, we would be at rest with respect to the ether, and it would not be possible to detect our motion relative to the ether. However, since the ether is the medium in which these electromagnetic waves propagate with a fixed speed, or that was what was speculated at the time, you would also see distant stars where the light from these distant stars would not be affected by the Earth's drag, because the Earth's drag would only act on the nearby ether. The light from those distant stars should experience an aberration. Okay, there would be a discrepancy in their positions due to the drag of the ether. No such effect or aberration was seen. So such alternative theories to explain the null result of the Michelson-Morley experiment also were contradicted by different experiments. This result was extremely puzzling to the physics community. On the one hand, you expected that Maxwell's equations tell you that there's a preferred rest frame in which the speed of light is c. On the other, Galilean relativity tells you that when you are moving with respect to this preferred rest frame, you should measure different velocities for light or different speeds for light in different directions. Yet, we could not detect the effect of these different speeds of light in different directions. How could this be?